Ah, Mr. McWilliams, I'm going to teach you guys plate tectonics. I don't know if you know it or not, but the Earth is broken into plates. So, we got the Earth. Well, the Earth is made up of 4 separate main layers. Very middle one's the inner core, and it's solid. Iron and nickel for the most part. Outer core is liquid. Mostly iron, that's where our magnetic field comes from. Next is the mantle. That's semi-solid, that has the ability to move. That little line right there is the asthenosphere, and that is pure liquid. These next 2 layers, the very top layer is a crust, just like the crust on pie. This layer right here is called the lithosphere, and the lithosphere is solid, and that's part of the plate that moves. These 2 put together, crust and the lithosphere, are what are called Earth's plates. Earth's plates are broken up into 13 main plates. These are the 13 main plates. You can recognize the United States here, or North America, Eurasia, Russia, South America. These lines right here are where the plates are broken up into different chunks. These plates here are moving apart. The red ones here are where they're moving together. And then there's transform boundaries where they move side by side, which is San Andreas Fault. But you can tell these plates are huge. This would be 6,000 miles wide, 7,000 miles long, and they're going to be 100 miles thick. So these things are enormous. Who knows what that would weigh, 100 mile thick rock, and how big it is. Now, the only thing that's going to move these things is something that's called convection cells. Convection cells basically heat that rises. It hits the very bottom part of the lithosphere and then drops. It rises, hit the very bottom part of the lithosphere, and then drops. The dragging of these convection cells, which is basically heat, and then when it cools, it drops, that's what drags the overhead plates and actually moves them. You'll get a crack right here. Chances are you'll get magma will come up and it'll make a mountain range here, which is called mid-ocean mountain range, or in the middle of the ocean. These convection cells are all through the Earth and what are making our different amounts of plates. Now, the deal with these plates is they move very slow. They move about the thickness of a paper a day. So that's whatever, that's probably about 8 pieces of paper right there. That'd be 8 days worth, 8 days of movement on these plates. So they're moving so slow, you can't even tell. So in a year's time, it'd be, 300, about an inch a year is what they'll move. So that's basically what plate tectonics is the outer crust of the Earth breaking up into plates that move separately. Usually when the plates are moving like this, you're going to get volcanoes in the middle of the ocean where it's going apart, or subduction where they're coming together, which you'll get explosions there as well as that's where you're going to get the majority of your earthquakes, because that's where the rock is moving. Now, in terms of these plates and their movements, there's 2 or 3 different things. How do we know they actually move? What's the evidence for it? Well, the first piece of evidence you can see right off the bat is South America looks like it fits in with Africa in terms of a jigsaw puzzle. Well, maybe that's just a coincidence, maybe it's not. Well, come to find out, they found a whole series of fossils, stubby-legged little lizard about that big, about that long, called Mesosaurus, on both coastlines, and the darn thing doesn't swim. So we know it didn't swim in the Atlantic Ocean. They had to have been connected together one time or another. That's one piece of evidence. The Appalachian Mountains start down here in Alabama, go all the way up here to Nova Scotia, They're also found here in northern Scotland and northern Norway. Well, the Appalachian Mountains didn't swim the darn ocean. That means these things were together, and then they broke apart, and the Appalachian Mountains moved apart. The very existence of the mid-ocean ridge system out here forming proves that these plates are moving away. As these plates move here, oops, I think that blue one's about dead. As these plates move apart here, and this plate moves apart here, you're getting a continual source of magma and deposition of magma at the bottom of these plates every time they move apart. So that's 3 pieces of evidence right there just off the top of my head. Hawaii is another one. Hawaii is a hot spot out here in the middle of the Pacific Ocean. There's a whole series of 6 separate islands out here. This island is the youngest island right here, and they get progressively older over here, so that plate's been moving over that hot spot the whole time. A hot spot is just a magma source that's centered in one spot, and the plate moves over it, and you just continually get the island going from that. So plate tectonics is the broken up of the plates. They move by convection cells. This is the interior of the Earth, inner core, outer core mantle, asthenosphere, lithosphere, crust, and these plates are moving from there. I'll cover one more aspect here, and then you guys can get started on your classwork that I want you to do this week, and that is the 3 separate type of plate movements that you can get. We talked about the first one, the very first plate movement that you can get. It's probably the easiest one to talk about is divergent plate boundaries. Divergent means they're moving away from each other. One plate's moving this way, one plate's moving that way. Once that occurs, this usually occurs in the middle of the ocean. That's why they're oceans actually, because these rocks are heavier, so they're lower than the continental rocks. Continental rocks are more buoyant, so they float above. You'll get something called mid-ocean ridge systems there, with this being the sea level right here. And you'll get a whole series of these leading out from that, away from these plate movements. That'd be convection cells moving right there. Divergence is very simple. The next one that you can get is we'll call transform plate boundary. Transform plate boundary is side by side. One plate's moving this way, one plate's moving that way. You don't get earthquakes with these, or I'm sorry, you don't get volcanoes with these, but you do get earthquakes with these. Because basically it's 100 miles and 100 miles and the darn thing gets stuck and it doesn't want to move. When the pressure builds enough, the plate breaks and it shakes. And that's all earthquakes are, it's rock breaking and the earth shaking. So you're going to get earthquakes with these on your transform. The third one we need to talk about is called subduction. Subduction is where one plate always subducts underneath another plate. Oops, just subduction. Subduction is where an ocean plate sinks underneath another plate, but the plate that subducts, this one, is always going to be the ocean plate because it's heavier. This could be continental above it, a continental plate, or it could be an oceanic plate. But either way, when this oceanic plate goes so far and goes so deep, it's going to melt. When it melts, it's less dense, so it'll rise. When it rises to the top, it's going to make a volcano. Booming, boom, boom, booming. And it'll blow up. These are usually found on continental edges. Occasionally they'll be offshore with ocean-to-ocean plate. It's called a volcanic arc, but don't worry about it for now. Just know these are the 3 main types: divergent, transform, subduction. Ocean plate will sink and form a volcano right there. That'll be a good enough start for this week, guys. I'll have you start the plate tectonic outline, and then we'll go from there. That'll work well.